Hey guys, hello everyone and welcome to the channel. So in this particular video I'm going to take 10 tricky questions from organometallic compounds. Now when I asked you guys in the previous post, many of you have asked me to make this 10 tricky questions on organometallic compounds, and I also thought that this is one of the most important topic if we talk about from the inorganic portion, right? So apart from coordination chemistry, organometallic is one of the most scoring topic which we have. So that's why this video is with you, and I'm going to take some questions which are going to be quite tricky. We are going to understand some new concepts. We are going to take some new types of questions, and we'll try to learn that how to solve them. Okay, so that's how this video is going to be. Now, before starting the video, before telling you anything about that, let me tell you that I'm teaching live on Unacademy platform. My classes are already running over there. Right now, I'm teaching for CSIR NET exam for the revision batch. For the next batch, for the new batch of CSIR NET exam, the classes will be launched very soon. And also, the classes for the upcoming GATE exams are going to be live on the Unacademy platform. So, do check out my profile on the Unacademy. And having said that, let's continue with our video. Alright, so let's take this particular question which was asked in CSIR December 2019 exam. The question was a 4-marker question, and the question says that the rate determining step in the catalytic synthesis of acetic acid by the Monsanto processes. Now, what is a Monsanto process and why is it used? You all should know that, okay? So the use of this Monsanto process is to take your methyl iodide and to convert this particular methyl iodide into CH3COI and plus water, and later on after hydrolysis of this, just to convert this into acetic acid, so CH3 C double bond OH, alright, and plus HI. That's what is going to be. So this is the Monsanto process in which we take methyl iodide and we convert that catalytically using the catalyst to form the acetic acid. That's what it is. Now once you know the basic of it, you should know the steps involved in the formation of this particular species. Okay, so basically what happens that when you take this methyl iodide and treat it with the Monsanto catalyst, which is basically your RHI2CO whole 2 minus, this particular species is a 16 electron species, and being a 16 electron species, this is electron deficient. In order to become 18 electron species, it can do like oxidative addition of this particular group on that. Now you know this is a hetero group or a polar group, so this is going to do a trans oxidative addition on it, and the product which you are going to get will be something like this RH, then you have CH3 and I on the axial bonds, and let's have the other groups on the equatorial bonds like this. Okay, so we have CO like this. Okay, so that's what we have got. Now once you have got this particular species, this is the first step which we have. Okay, so the attack of methyl iodide on this particular reagent or in this on this particular catalyst is the first step, and this is oxidative addition, and that to a trans oxidative addition. In the next step, since it has now become a 18 electron species, and since you have methyl group as well as you have carbonyl group in the same molecule, so the next basic thing which can happen is your migratory insertion. What type of migratory insertion? So one migratory insertion in which this methyl group is going to get, like this carbonyl is going to get like migrate, and it is going to come in between of metal and alkyl bond. Okay, so basically you are going to get something like this, that is CH3 C double bond O, and you have RH CO I and you have I. Alright, and apart from that you have a vacant site created at this particular place. Now once this vacant site has been created, in the next step basically you can add a carbonyl group to this. So this carbonyl will come and is going to get bind to this particular position, giving you this species. It's going to be RHCO C double bond OCH3, and then you have I, you have CO, you have I, and you have I. Alright, so that's what is the species which you have. In the next step is going to be like the further step is going to be your reductive elimination, and this group, okay, which is going to be cis to each other, are going to get reductively eliminated. So reductive elimination is going to be the next step, and which is at the end going to give you the catalyst back, that is RHCO2I2 and with a minus sign, and along with that you will get CH3 C double bond OI, and that's what we can be converted into acetic acid after the hydrolysis. So that's what I have already told you. So the question was that what is the rate determining step? So the rate determining step in the Monsanto process is the attack of, or the oxidative addition of the methyl iodide on the catalyst, and that is because it totally depends upon the electrons density on the metal surface of the catalyst, that how this particular CH3I or how this reagent is going to attack on that. If instead of RH we would have taken some other metal, for example of the same group, if we would have taken cobalt or if we would have taken iridium over here, then the rate would have been faster or slower, right? So in this step, the rate determining step, or in this reaction the rate determining step is the first one. So oxidative addition of methyl iodide to this methyl iodide to RHI2CO whole twice minus is the rate determining step for the particular reaction. So the correct answer goes your option number 1. Alright, so you should know about the whole process, like whole Monsanto process, that what actually happens, and once you know that, you should be able to find out that what is the rate determining step and which is not. And this is the slowest step, okay? The rest of the steps are faster and they are not your rate determining steps. So this is how this question has to be done. Alright, now let's take the next question then. Alright guys, let's try to look for this particular question. This was again asked in December 2019, and this was again a 4-marker question. It says that the cluster type is Fe5CO14N minus and CO6CO13N minus. They're asking that what type of cluster they are actually. So let's try to do it. So basically the method of doing is to calculate the polyhedral electron count, okay, or skeletal electron pair, whatever you call it. So that is calculated as your 12 into n minus total valence electrons, and you divide this whole value by 2. So this particular thing, this basically polyhedral electron count is just 12 into n minus total valence electron. You can call it as a skeletal electron pair, okay? So that you will get as 12 into n minus total valence electrons divided by 2. So once you get this whole value, let it be x, okay? You got x over here. Now if x is like n plus 1, where n is the number of metal centers, so then it is called as closo. If x is equals to, okay, n plus 1, if it comes out n plus 2, it's nido. If it is n plus 3, it's arachno, and so on, okay. N plus 4 is closo, nido, arachno, hypho, okay, and so on. So now let's try to check out our options. So the first one, when you will do this, so this is Fe5 and CO14 and N minus. Now let's try to find out the total valence electrons first of all. So the total valence electrons will be like one iron species is going to have 8 valence electrons in it, right? So 8 into 5, okay, so 8 multiplied by 5 and plus 14 into 2, because each carbonyl donates 2 electrons, and plus the nitrogen gives 5 electrons as such, okay, so 5 electrons from nitrogen and plus 1. So if you calculate this makes it 40 and this makes it 28. So 40 plus 28 is 68 and plus 1 is 16 and plus 5 is 74. So it comes out 74 as your total valence electrons. Now once you calculated this, the next thing is to calculate your skeletal electron pair, and that can be calculated as 12 into 5 and minus, or basically you can do it in this way, because that is going to give you a bigger number. So total valence electron minus 12 into n, okay, and divided by 2. So this is going to give you 74 minus 12 into 5, because we have 5 metals, so that is going to be 60 divided by 2. It's going to give you 7. Now 7 you can write down as 5 plus 2, so it comes out of the order n plus 2, so this became nido. Okay, so the first crystal or the first complex over here is a nido complex. Now once you have got this, it's pretty simple to do the next part. Okay, let's try to do it. The next part over here is your CO6, then CO13, and then N minus. Okay, so find out. So from the each cobalt you are going to get 9 electrons, so it will be 9 into 6 and plus 13 into 2 and plus 5 and plus 1 because of the negative charge. Count that out. 9 into 6 is going to give you 54 and plus 6 is going to give you 60 and 13 into 2 is 26. 60 plus 26 makes it 86. Okay, so 86 is total valence electron. Now skeletal electron pair when you calculate, so that is going to be 86 minus 12 into 6, right, and divided by 2. So 12 into 6 is going to give you 72 divided by 86 is going to give you 7, right? So you are going to get it as 7. So 7 can be written as n plus 1 here. Why? Because the metal over here are 6. So 6 plus 1 gives you 7. So this became closo. So this particular structure is basically closo. So your correct answer comes out option number 2. In the CSIR NET answer key, when it was when the answer key was published, the answer was nido and nido as per their answer key. But as per the reference and as per the method, it goes option number 2. Later on, I guess the answer has been corrected. If it was not corrected, do let me know in the comment sections, okay? Because as far as my knowledge, the answer earlier in the answer key was nido and nido, and later on in the updated answer key, they changed it to nido and closo. Alright, so this is how it will be done, and the correct option will be your option number 2. This is the method to do for the cluster complexes, to find out closo and nido for that. Now let's do the next question. Alright guys, let's look upon this particular question. This was again asked in CSIR December 2019, and it was a 4-marker question. The question says that the main product of the nucleophilic attack of proton, basically it's not proton, it's nucleophilic attack of hydrogen ion, H minus and hydride ion on the complex ion given below. The ion was given to you and it says that which of the following is going to be the product. So basically nucleophilic attack on the polyenes is calculated using a rule called as a DMG rule. Okay, so DMG rule I will tell you in very short over here. The points which I am going to tell you will help you to solve any questions related to DMG rule. Okay, so you will be able to do those questions over here. So the rule has 2 parts. First of all, this rule is used for 18 electron polyenes. Okay, the clusters which have 18 electron polyenes. Okay, so first thing is that. Now there are 2 parts of it. The first part is that the first part of the rule, it says that even polyenes, okay, will undergo nucleophilic attack much faster as compared to the odd polyenes. Okay, so this first line or this first rule tells you about the who goes first. Okay, so it tells you about the priority of nucleophilic attack. So you have to give more priority to the even polyenes. The second rule or the second point of this DMG rule, it says that basically acyclic polyene will undergo nucleophilic attack much faster as compared to your cyclic polyene. So now if you look upon the question, if you look upon the given molecule which was the polyene which was given to you, here you have hapticity of 6, here you have hapticity of 4, here you have hapticity of 3. So it says that even polyenes will undergo much faster attack. So you can just cancel out this. This is not going to undergo nucleophilic attack. These two have more chances of undergoing nucleophilic attack. Now out of these two, this is acyclic and this one is cyclic. Now you know where the attack will be, right? Cyclic one will be like acyclic one will be much faster as per the second point. So that means this particular ring is going to undergo nucleophilic attack, and this is because we are doing a hydride attack, so its hapticity will change from 4 to 3, and that you can see in option number 2. This is the option which will be the correct option. Now if you look upon the other options like option number 1, which says that the nucleophilic attack of the first or the cyclic polyene, that is not going to happen because acyclic you have to give more priority. Here again they have done the nucleophilic attack on the odd polyene, which is not correct, and same goes over here. They have attacked on the odd polyene, which is not going to be correct. Okay, so the correct option as per the DMG rule is your option number 2. All right, so this is how we have to do questions from here. Now let's look upon the next question then. Alright guys, let's look upon this particular question. This was again asked from your December 2019 exam, and it was again a 4-marker question. And let's try to look upon this. This question is very good. Okay, you can do these types of question from a very simple trick which I am going to tell you in this video. So it says that the correct order of metal carbon distance or metal carbon bond length. So in order to answer this type of question where you are given with the ferrocenes or metallocenes and you have to find out metal carbon distance, there is a simple trick which you can use. Okay, so the simple trick or the simple concept which you can use goes in 2 points. Okay, the first point says that like you have to look for the unpaired electrons. Okay, if the number of unpaired electrons increases, in that particular case what is going to happen? If the number of unpaired electrons increases, in that case metal carbon bond length, okay, metal carbon bond length also increases. So you just have to look for the number of unpaired electron. Now where you have to look for number of unpaired electron, that is very important. Okay, so you have to look for that in the molecular orbital diagram of your metallocenes. So the metallocene, in the metallocene, d orbital splits in this particular manner. Okay, so the d orbital splits up in this manner. The lowest energy orbital is basically like two-dimensional, or you can say that a doubly degenerate energy level, and this is your dxy and dx square y square. The next orbital is going to be dz square, and then the highest energy orbital is going to be dxz and dyz. So this is how the d orbital splits. Now if you look upon the species, like the given species which are given to us in the given question, we are given with Ni and eta 5 Cp whole twice, then we have Co, eta 5 Cp whole twice, then we have Fe and eta 5 Cp whole twice. You have to just look for the d orbitals because there is no charge on the metal surface, so just leave that. Okay, so nickel is going to be a D8 species, right? So you have to fill 8 electrons in this case. So let's try to fill that in the molecular orbital diagram. So we'll fill it like this: 1 2 3 4 5 6 7 and 8. This is how we are going to fill it. So the number of unpaired electrons, okay, so unpaired electrons over here are going to be 2, because you can see these are 2 unpaired electrons. In the case of cobalt, if you see, so this is going to be a D7 species, right? Cobalt in the zero oxidation state is a D7 species, because we are just filling electrons in the d orbital. So basically what will happen, that one of the unpaired electron will be reduced, right? You will have one less unpaired electron here. So the number of unpaired, so this is how it will be filled: 1 2 3 4 5 6 and 7. So the unpaired electron over here, unpaired electron will be just 1. And same if you go for this ferrocene, in that particular case you just have a D6 species. So here this particular unpaired electron will vanish, and you will just have 1 2 3 4 5 6. So basically the number of unpaired electrons are going to be 0. Now as I told you that as the number of unpaired electrons increases, metal carbon bond length also increases. So the highest bond length will be in nickel complex, then cobalt complex, and then iron complex. Your correct option goes with the option number 4. So like that, you can do any question which is asked on the basis of metal carbon bond length, and if you are given with metallocene. So this is the basic concept which you can apply to solve questions like this. All right. So I hope this was much clear to you. You guys understood well that how we have done this. Now let's go for the next question then. Alright guys, let's look upon this particular question which was asked in CSIR June 2019 exam, and this was asked for 2 marks. Okay, it seems pretty simple question, but yet people did mistake in it. The question is that the number of nickel-nickel bond length in CpNi mu ppH2 whole twice is, okay, complex O being 18 electron rule. So in order to find out number of metal bonds, first thing is to find out the total valence electron. The complex given to us is CpNi mu ppH2 and whole twice. So total valence electron goes like this. Cp is basically your cyclopentadienyl ligand, which gives you 5 electrons towards the metal center. Nickel is going to be a D8 species, 2 electrons from the S, so 8 plus 2 means it's going to give you total 10 electrons in the neutral atom method. Mu over here, mu ppH2 gives 3 electrons, okay, remember that. So I'm just writing here, okay, mu ppH2 is a 3 electrons donor, whereas Cp, because its hapticity is 5, so it's a 5 electron donor. So let's write down 3 electrons for that, and I'm going to multiply whole by 2 because whole twice is there. So when you do that, you are going to get actually 18 into 2, that is 36, right? That's what you got. Now in order to find out number of metal bond, basically the formula goes like this. It is 18 into n minus the total valence electron divided by 2. So that's how we calculate it. So 18 into n is 2 because total you have 2 metals, and minus total valence electrons is 36 divided by 2. 18 into 2 is 36, 36 minus 36 is 0, 0 divided by 2 is 0. So you're not going to have any metal bond. So how does your complex is going to actually look like? So let's see that. So you will be having nickel, and you are going to have the other nickel. Since you have bridging ligand, so ppH2, and that's how it is going to be. Cp is going to get attached like this. Okay, so this is going to be the structure of the complex, and that's how it is going to look like. So 0 metal bonds, option number A is the correct option for this. Alright, I hope this is much clear to you. Now let's go to the next question. Alright, let's try to look for this particular question which was asked in CSIR June 2019 exam, and this was again a 2 marker question. The question is pretty simple. It says that for the reaction of trans IRX COPPH3 whole twice, where X can be fluorine, chlorine, bromine or iodine, with oxygen molecule, correct order the variation of the rate with X is. So let's first of all look at actually what is happening in the reaction. So basically the molecule which is given to you is a trans molecule. Here we have PPH3, we have PPH3, we have CO and X. Now when you are treating it with oxygen O2, so what is going to happen? Basically a oxidative addition reaction is going to happen, and you are going to have iridium. Rest of the thing will remain as it is. So basically one oxygen here and the other oxygen, a cis addition of oxygen is going to happen because it's a non-polar molecule, right? And then you have X, you have PPH3, you have CO, and you have PPH3. So that's how it is going to be. The reaction is going to be, okay, these are on the plane groups. Okay, so yeah, that's what it is. Okay, so this is how the reaction is going to be. Now you have to talk about the rate of the reaction with respect to X. So what has happened, which reaction has happened? So let me write down, this is oxidative addition reaction. Okay, addition reaction. Now the rate of the oxidative addition reaction, let me write down few points. So rate of oxidative addition reaction, how does it depends? The first point which affects it is the electron density on the metal. Okay, electron density on metal. So if electron density on metal basically is directly proportional to your rate of oxidative addition. So if you have more electron density on the metal, you have high rate of oxidative addition. If you have less electron density on the metal, you have less rate of oxidative addition. That's the point. So what actually these groups are doing, so you have to understand just one point, that an electron withdrawing group, okay, on metal, what it is going to do, this electron withdrawing group on the metal is going to decrease electron density on metal. Okay, it's going to decrease the electron density on the metal, and if it decreases that, so basically the rate of oxidative addition also decreases. So that is how the whole thing is actually related to. So the one which is having the high electron withdrawing nature among the other x's is going to decrease the electron density more, and it's going to like decrease the rate of oxidative addition. Okay, it's going to decrease the rate of oxidative addition. So just let's write down the rate of electron withdrawing nature. So electron withdrawing nature, okay, electron withdrawing groups, if I talk about, so fluorine is the highest electron withdrawing group, then chlorine, then bromine, and the least one is iodine. So if I talk about the rate, so fluorine is going to decrease the rate highest. Okay, so it's going to decrease the rate up till the highest value. So rate ka order is going to be reverse of that. Okay, so fluorine will have least rate, then chlorine, then bromine, and the highest rate will be with iodine, which has the least electron withdrawing nature. So least electron withdrawing nature, highest rate of the reaction. So that's how your answer will be your option number D. Okay, so the electron withdrawing nature is the answer, or it's the reason for the answer of this particular question. I hope this is much clear to you. Alright, so let's go for the next question. Alright guys, let's look upon this particular question. This seems to be pretty simple, but it was a tricky question. It was asked in June 2019 exam, and it was again a 2-marker question. The question says that the organic species isolobal with this, okay, the species which is given to me is FeCO hold twice, then PPH3, and then I have minus sign. So isolobality, you know, it's pretty simple. If something is having 14 electrons in the transition metal complex, so that is going to be isolable with 4 electron species. 15 electrons is isolable with 5 electron species. 16 electron species is going to be isolable with 6 electron, and so on, right? 17 electron is going to be isolable with 7 electrons. So you know this thing, okay, these are transition metal fragments, and these are main group elements, or main group fragments. If you look upon here, the total valence electrons which you are going to get is iron is going to give you 8 electrons, D6 and 4s2. So 8 electrons here plus 4 electrons from the carbonyl ligand plus 2 electrons from this PPH3 ligand, and plus 1 because of this negative charge. So overall, if you count it, you are getting 15 electrons. So a 15 electron species has to be isolable with a 5 electron species. Now among the options, you have to see how many electrons you have in each of them. So this is CH2 plus. So carbon gives 4 electron, 2 hydrogen gives you 2 more. So 4 plus 2 is 6. And this positive sign means 1 electron is less. So this is a 5 electron species. The next one here, if you see, carbon gives you 4 electron, then 1 from the hydrogen and 1 from the negative charge. So you have got 6 electrons in this. Here you have got 4 from carbon, 3 from hydrogen, so 7 electrons. Here you got 4 from carbon and 1 from hydrogen. So you got 5 electrons. Now that's what the question was about. Like, people got confused that which one they have to take as isolable, whether A or option number D. Now here you have to look for the other, or the second definition of the isolability. The first thing is that the number of electrons should be same. The second thing is the shape of the frontal molecular orbital should be same. Now this, if you see this FeCO PPH3 minus, it's basically a fragment taken from the octahedral complex of iron. Okay, so 3 of them are coordinatively done, but 3 spaces are empty here. So iron basically Fe, and here you have CO and PPH3. It has 3 vacant fragments. Okay, these are 3 vacant fragments. And if you look upon this CH group, so here also like because carbon has 4 valency, so it has 3 vacant sites. But if I talk about this CH2 group, so here you have like carbon is attached with two hydrogens, and it just has 2 like fragments which are vacant. So based upon the like vacant fragments, the correct option is option number D. So this is what I wanted to convey to you, that in case you get something like this where you are not able to like tell the correct answer based upon the valence electrons, in that case look for the fragments also. Okay, look for the vacant orbitals also, look for the orbital sizes also. So that's how the option will be done, and the correct option was option number D. Alright, now let's take the next question. Alright guys, let's look upon this particular question. This was again asked in CSIR June 2019 exam, and this was a 4-marker question. Okay, the question says that the possible structure of the intermediate involved in the following reaction. The reaction is given to you. They have asked which is the following, like which is the intermediate. So let's draw the reagent first of all. So it's eta 5Cp. So this is what we have, and then we have, with this we have CO and CH3. So if you look upon this species, this is a 18 electron species. Now since you are reacting it with PPH3, so it won't directly attack over here unless and until you create a vacant site. So for that, just understand this, that in a like in organometallic fragment, if you have methyl group as well as carbonyl ligand both, then there are high chances that it is going to undergo like migratory insertion, 1-1 migratory insertion. So the first thing which is going to happen is 1-1 migratory insertion in this. So this methyl group is going to like it's going to migrate, and what you are going to get is Fe, and then you have CO, and then you have C double bond O and CH3 and a vacant site. Now this vacant site will be filled by your PPH3 in the next step, right? So PPH3 is going to attack, and the final answer is going to be something like this: Fe, and then you have CO, then you have C double bond O CH3, and then you have like PPH3. Okay, so that's how the reaction will happen. But the intermediate is the one which has COCH3 and CO attached with the metal and with a like with the cyclopentadienyl ligand. So that's option number 3. So it was pretty simple and pretty straightforward reaction. You just need to know that where migratory insertion happens and what are the conditions for that. Alright, so this is how it has to be done. So I hope this is much clear to you. Let's go for the next question then. Alright guys, let's look upon this particular question. This was again asked in CSIR June 2019 exam, and it was asked for 4 marks. Okay, so let's look upon that how to solve this. It says consider the following reactions: A, B, C. These are the 3 reactions given. It says the reaction which will not produce ethane as a product. Okay, so where you're not going to get ethane as the product. So to answer these questions, you have to be very good with the reaction mechanism. You have to good with oxidative addition, reductive elimination, beta hydride elimination. You have to good with those things. So I'll start from the very easy one. The easiest one is option number B. You can see that here this particular group can undergo reductive elimination, and basically it can give you like ethane group, that is CH3, and later on the oxidative addition of this group to like methyl iodide to this is going to give you this complex. So PPH3 and CH3 and I. Okay, this is what you are going to get. So oxidative addition of this and reductive elimination of this, but the first step will be oxidative addition because it's a square planar complex, 16 electron species. So this is going to do the trans addition, and then these two groups being cis on each other are going to undergo reductive elimination and going to give you ethane. Now it was asked which is not going to give you ethane. So option B you can cancel out because here you are getting ethane as a product. So just cancel out that. Now you are left out with option A and C. So let's look upon option number A, whether it is or not. So if it is so, then you can go with the answer very easily over here. So let's see that what happens in this case. So let me draw the molecule first of all. So I am having P and PH2 and PH2, and I have PT here, and I have CH2 and CH2. Here I'll write down this as this CH2 and H. Okay, so that's how I have written it. So So basically the first thing which will happen is beta hydride elimination. This hydrogen is going to go here, this bond is going to break. So what you are going to get is beta hydride elimination, and with that you are going to get something like this: P and P, PH2 and PH2, and then you have PT here, and then you have H, and then you have CH2, CH3. Okay, so that's what you have. Along with that, what you are getting in this step is a removal of your CHO. Okay, so that's what is the group, formaldehyde group is going to leave the reaction. In the next step, what will happen, that reductive elimination will happen for these two groups, and they are going to get reductively eliminated, and it is going to form a ethane group. Okay, so you are going to get CH3 and CH3 group. So this is basically forming a ethane. So option A is the one which forms ethane. So the question says which does not produces ethane as a product. So A produces, so you can cancel out option number A, as well as you can cancel out option number D, because there also you have option A or reaction A given. So correct option comes out to be option number C. Now in option number C, you might be thinking, why not it is undergoing reductive elimination like this, okay, and it's making ethane. It seems pretty simple, right? It looks very straightforward like this, but the reaction does not happens like that. I'll show you the complete mechanism of it, that actually what is happening in it. So if you look upon this reaction, this is how, and this is what it is given. The first step basically is your ligand displacement, okay, ligand displacement reaction. So in this reaction, this PPH3 is going to leave the bond, and this particular thing or this particular ligand is going to bind through the pi bond. Okay, so what you are going to get is something like this, CO, and here you have CH2 double bond CH2, and then you have CH3 and you have CH3. So this is what you are going to get in the first step. What is the reaction? What's the driving force of this reaction? It's because of the pi bond with this ethene group, which is going to be more stable rather than this. Okay, so it's not a stabilized thing. So if you look upon the species over here, it's, although it's a 18 electron species, yet this PPH3 ligand with the metal is not forming a stable or a strong bond. So that's why it has underwent the ligand displacement. This particular bond is now quite more stronger as the previous one. In the next step, what is going to happen is called as your migratory insertion. What kind of migratory insertion we are going to see is called as 1,2 migratory insertion. Okay, so let's see what is going to happen over there. So in that case, this is called as carbon 1, this is called as carbon 2. Migratory insertion of this methyl group will take place, and basically you are going to get something like this, CO, and with that you will have CH2, you will have CH2, and with this you will have CH3 attached, and here this CH3. So what has happened, that this methyl group has went, or it has migrated on this particular carbon. So that has happened in this particular step. Now I'll just modify this particular thing a little bit, so I can write down it as CH and H. In the next step, I'm going to have beta hydride elimination reaction, and in this what will happen, that this alpha and this beta hydrogen is going to combine on the metal, and this bond is going to move like this, just like we have seen that removal of formaldehyde group. In the same way, the reaction is going to happen over here as well, and I'm going to have CO, with that H is there and methyl group is there, and along with that the other byproduct which I have formed is actually your CH2 double bond CH3. So propene is what has been formed. In the last step, if I am doing reductive elimination, so what it will be formed as the final product? So basically methane, CH4 will be my final product, not ethane. In the question it was asked key which will not produce ethane, so that's your option number C, and that's your answer, or the option number C is going to be the correct option for this particular reaction. Alright, so this is how it has to be done. You have to be very good with the reductive elimination and all the basic reaction mechanism of organometallic compounds. You should be aware about all of them. Well, that's it from my side, guys. Thank you so much for watching this particular video. I hope that whatever we have discussed in this video was helpful to you. You guys understood it well. If you are new to this channel, if you have not subscribed the channel yet, please subscribe to it. If you like this video, give it a like, share it with your friends, because sharing is caring. So make sure you subscribe the channel, make sure you like the video, make sure you share it with your friends. Also, we have pages on Facebook as well as Instagram. So if you are there, if you want to connect on the other social platforms, so you can connect with us on Facebook and Instagram both. The handle is @chemoholic. You can search for that. The page name is same, that is all about chemistry. So do follow me, do follow this particular channel on Facebook as well as on Instagram. All the detailed links are there in the description of this video, so do check that out as well. Thank you so much for watching and have a great day. Bye bye.